from this covariance matrix. 1,000 by 1,000, right? Then, like I said, we compute the eigenvalues of this matrix, which will give us 1,000. We sort those. We pick the top 200. Corresponding to 200, we now create vectors and put them side by side. 1,000 by 200. So here's 1,000. Here's 1,000. So this will be 1,000 times 200. Let me call this EV matrix. You can call it anything you feel like it, but short for eigenvectors. Okay. So now let's go back, and we need a few more steps over here to reduce the dimensionality. Okay, so now what we'll do is we'll create basis vectors for the reduced 200-dimensional space. Okay, so if you take a look at our original mean adjusted data, right? What was the size of it? 784 by 1,000, right? And so if I do now, I had transpose. Okay, so this will become. Sorry, let me see, 1,000, no, my mistake over here. If I go over here, okay, I need to do 1,000 by 200, and our training data is 784 by 1,000. Okay, so, okay, if I did this, if I did EV transpose times I hat, so then this one will be
1,000 cross
200 cross 1,000, right? Because I did a transpose. And then this is
784,000.
sorry, my mistake. One more time. Okay. Let me just do a simple. I hat, which is 784 by 1,000 times EV, which is 1,000 by 200. So what will we get?
784 by 200.
We'll get a matrix 784 by 200, right? So there will be 784 of these and 200 of these columns. Okay, so this is what we call the basis, okay? So suppose I call this the B matrix, the basis matrix. Okay, okay, so remember the goal is every data in the original space has 784 values to it. We want to reduce it to 200, right? So now let me show you how will we do that. After we have the basis matrix, then now if I go, okay, and if I do I is 1,000 by 784, so we have 200 bases, okay. Suppose I pick like this. Suppose I pick I0, meaning the first column out of the mean adjusted, right? Wouldn't that be 1000 by 1? Sorry, 784 by 1. Okay, and if I multiply it by the bases, B matrix is 784 by 1000. So what I will need to do is I need to take the transpose of this, multiply it with the B matrix. So B matrix is 200 by 784 by 200. Okay, so this one I took the transpose, right? This will become 1 by 784. So what will be the result?
1 by 2.
It will be 1 by 200. So the original I0, which was in 784 dimensions now, do you see then now it's reduced to just 200 numbers? Same way you can pick any input data. So it could be I5, I87, I32. All you have to do is multiply it with the basis vector, and you will get 200 numbers, which is the 200 dimensional representation of the 784 original dimensions. And so this is how we are able to automatically keep the most important information by reducing the original input from 784 to just 200. Okay. So that's the idea in principal component analysis. I'll give you a little more intuition in a second, but let me first at least show you what's the procedure. Okay. Procedure is our input data. We had 1000 input data. Each was 784 pixels, right? So our input data I was 784 by 1000. Then what we did is found the mean of each row and subtracted from every column. And so that became the mean adjusted data, 784 by 1000. So it's still the same size as the input, but mean has been shifted. So once again, if the data was somewhere over here, data has been shifted around the origin. Okay, so that was easy. Then from here, we do the transpose time this, so that we can create a square matrix 1000 by 1000, which we call the covariance matrix, because inside it, there's a relationship of each data to every other data to see how the relationship between mutual data is. I mean, one to another data is. Then for this one, we create the eigenvalues and eigenvectors. So this one will give us 1000 eigenvalues. Of course, if we took for every eigenvalue, there's an eigenvector, that will be 1000 by 1, and there's a standard procedure for creating those eigenvectors, right? Because we wanted to reduce to 200 dimensions, so we sort the eigenvalues, pick the 200 highest of these because they have the most amount of information. Okay, once we have that and we assemble it into an eigenvector matrix, that becomes 1000 by 200. So now from here, we create what is called the basis vector. So the basis vector is simply the mean adjusted data projected onto this 200 eigenvectors. As we do that, we get our basis. Okay, and I'll clarify this basis a little more in a second. Then, once we have the basis, then any input data, for example, I0 or I5 or whatever, all we have to do is just take the transpose of that data, multiply with the basis to reduce it to the 200 values. So now any data can be reduced to just the 200 values, right? Okay, let me clarify the basis a little bit more. Okay, so one of the fundamental concepts in math is orthogonality. Okay, suppose you are given some function fx, some function g of x. Okay, for them to be orthogonal, if we integrated from minus infinity to infinity, and see, think of it this way, what is integral? Isn't that the area under the curve, right? So if, let's say, f of x looks like this, if g of x looks like this, so if this is f of x, this is g of x, if I multiply the two and integrated it, for orthogonal, this has to be 0. Okay, my question is, if f looked like this, g looked like this, are they orthogonal to each other? No, you can easily visually see, because as we multiply and integrate, the area will be like this, so they're not orthogonal. On the other hand, what if I have, let's say, some function like this, another function like this. So this is f, this is g. So g is this, f is this. Are they orthogonal to each other? Yes, right? So that's for continuous functions. For vectors, how do we know whether two vectors are orthogonal to each other or not? See, orthogonal also means 90 degrees in plain English, right? So for example, if I have an x-axis, y-axis, right? If you take a look, pretend this is z-axis. If I have a 1 point on the x-axis, and let's say x of 1 on the x-axis, how will I represent it as a vector?
1, 0, 0.
X, y, z, right? 1, 0, 0. Now let's say I have another point on the y-axis at 1. How will I represent it?
0, 1, 0.
So this one will be 0, 1, 0. So my question is, visually you can see, are they 90 degrees? But mathematically, how do we show that they are orthogonal? Okay, the integral becomes a summation in the discrete world, right? So if we did an inner product of these two, so you did a 0, 1, 0, inner product 1, 0, 0, right? 1 times 0 is 0, 1 times 0 is 0, 0 times 0 is 0. Now you add all of these. What number will you get?
0.
So are they orthogonal?
Yes.
So these two vectors are orthogonal, right? Okay, so we refer to these as basis vectors. Okay, very similarly on the z-axis, what will be our basis vector? 0, 0, 1. Everybody agrees? So why do we care about orthogonal or the basis vectors? Simple. Okay, if we have basis vectors, and especially the orthogonal basis, then any vector can be created as a linear combination of basis vectors. So let me give you an example. Suppose somebody gives us a point 2, 3, 5. So let me show you how this will be represented as a linear combination of the three basis vectors, right? 2, 3, 5 can be written as 2 times the basis vector on the x, which is 1, 0, 0, plus 3 times the basis vector on the y, which is 0, 1, 0, plus 5 times the basis vector on the z-axis. So 2, 3, 5, 2 multiplied by the first basis vector, 3 times the second basis, 5 times the third, is our, any data in our three-dimensional space could be represented as a linear combination of the three basis vectors, right? Okay, so very similarly, let's go back to our problem. Okay, our problem is we have a 28 by 28 digit, right? For example, 2. What dimensional space is this data in? 784 dimensional space, right? So suppose somehow we come up with 200 basis vectors. See, once again, think of it this way. In the 3-dimensional space, what was the size of each basis vector? 3 by 1. So in the 784, if I say there are 200 basis vectors, what will be the size of each basis vector? It will be 784 by 1. Right? If I put all of these side by side and assemble it into a B matrix, what will be the size of that matrix? 784 by 200. So take a look over here. Once we came to the basis vector, what did we come up with? 784 by 200. Okay. So now the next step. Once we have 200 basis vectors, what's the next condition? They should be orthogonal to each other. And for orthogonality to be verified, what will we do? Pick any two of these vectors. If we did the inner product of those, it should be 0, right? So if you can take my word for it, those of you who in computer vision are actually doing the whole step by step, you can easily go pick any two of these 784 by 200. Pick any two. Maybe pick the third column. Maybe pick the 8th column. It doesn't matter. If you did an inner product, element by element multiplication, and added the numbers, what will you come up with? 0. So that's the beauty of the principal component analysis. Principal component, think of it as giving us the basis vector. And you decide how many dimensions you want how many basis vectors you would want. It could be 200. If you wanted to reduce it to 100 dimensions, you can pick 100, okay? Okay, once we have the basis vector, okay, then any high dimensional data, meaning any 784 dimensional data, can be projected onto this basis vector to find out what are the 200 coefficients, what are these, just like in the 3-dimensional case, 2, 3, 5 were the coefficients representing the actual data in terms of those basis vectors, right? So take a look over here. So if I go, okay, if somebody gives me I unknown, so they gave us a digit. The digit may look something like this, right? But we don't know whether it's a 3 or not. They just gave us a picture. What will be the size if we went to every row, every column, assembled into a matrix? What will be the size of IX? 784 by 1. Now let me ask you the next question. I want to reduce it to 200 dimensions. How will I do it? Multiply with the bases, exactly. So this is 784 by 1, right? So if I did IX transpose times the bases, so this will become 1 by 784, right? Times 784 by 200. Won't I get 200 numbers, meaning 1 by 200 matrix? So you see how easily once we have the bases, just multiply it with the bases and you will get the 200 reduced dimension. So 784 dimensional data has been reduced to 200 dimensions. Okay? So computing the bases is a one-time process. Okay? And notice once again, when we computed the bases, did we care about whether the input data belongs to the digit 2 or digit 3? No, not at all. We took all the 1,000 data points, assembled it into the matrix, all the 1,000 digits, mean adjusted it, okay, found the covariance relationship of one data to another, then the highest eigenvalues of the covariance matrix tell us that that particular eigenvector has the most amount of information. Once we have those 1,000 by 200, those eigenvectors, then we use that to compute the basis. Take the input data that's given to us, multiply it with the reduced eigenvector matrix, and that gives us the basis. Once we have a basis, extremely simple from that point on. Any input data, multiply it by the basis, and you will get the 200 dimensional reduction of that, right? So now let me explain what you will do in your next assignment to really understand it, the motivation behind it. So this is what you will be doing. Okay, you don't have to program the eigenvalues, eigenvectors. There's a very easy scikit library in Python. Computing the PCA is one line of code. Okay. So in this course, I don't want to, have you suffer through. However, if you're taking computer vision, I want you to understand it completely. So you won't use the library. You will go through your manual computation of the eigenvalues, eigenvectors, and so on. Yes.
So I have a question for that. So for doing mean adjustment, rather than the training data, if you go with the test data, the training data is more accurate to the mean, right? So we'll get more error, I feel.
Yeah, for the test data, the mean may not work out as well, but it's pretty close. So that's why having the more data you have, the more accurate it will behave. Because if you took an average over, let's say, million data points, even if something is unknown, it will still be very close. But if you only had a data of 30 data points, you took the mean and unknown data comes in and it's far off, it will not work. So the more data is better. Yeah. Okay, so now let me explain what you will do. So what I wanted you to understand is, the universal approximation theorem, remember, said more than one hidden layer is useless, okay? However, if we use the extra hidden layers for something else, not for the purpose of creating a classification boundary, but for enhancing the data, then it really will help us in the final accuracy, and you guys will verify it yourself. So, two options for enhancing the important features inside our data. One was PCA. And then I'll come to the second point where we will not use the PCA, we'll get even something better with a deep network. Okay? So in the assignment, you will use scikit library for the PCA. Don't worry, I'll give you all the skeleton code so that your goal is as easy, your job is as easy as possible. So this is what you will do. You will take the 784 by 1 data, and of course 1,000 of these. Okay, you will go through a PCA. Okay, then you will compute the basis over here. Okay, once you have the basis, then like I said, any unknown data can be simply multiplied by the basis to reduce it to 200, right? So So let's say we've already done this. We have the bases, any data that comes in, we multiply by the bases, then this gives us 200 by 1 data, right? So 784, as we pass through the PCA, gets reduced to 201, okay? Then we'll connect it to our 200 or 100 neurons. It doesn't have to be 200. So all of these will basically go to each and every one. Okay, and then 10 neurons as an example. And softmax over here is your output. Okay, so once you train this system, you'll fix the weights, then you will test it on the 10,000 test data. The same thing, you will go to the PCA bases that you already had computed, pass it through the hidden layer, and so on. And I forgot if originally you were getting 90% accuracy. As you go through the PCA, it may get 92%. So you will see an improvement. Okay. So essentially what the PCA has done is, it has basically taken the 784, as we already discussed in this 784, there were a lot of dark pixels which contribute absolutely no value to the recognition. So PCA, rather than us telling us which pixel to use, which pixel not to use, is learning from the test data, figuring out what is the important 200 numbers that represent this data, and that we will use to train our classifier, and it will do a better job.
What is the possibility of eliminating unnecessary data rather than doing PCA? It's actually doing on its own. Do we have any possibilities of just eliminating the unnecessary data?
So one was the PCA, right? Because PCA automatically is telling us, hey, these 200 are the most important numbers that represent the 784 data. Right?
But
So it's implicitly doing it, right?
yeah, it actually categorizing it, right?
No, it's not categorizing it. It's simply telling us out of the 784 data, these 200, not necessarily one-to-one, but these are the 200 numbers that represent the 784 data almost better than the original data, because it's picking out the most relevant information in it. Okay, so anyway, so like I said, you will try it yourself. I'll give you all the skeleton code and it will help you learn that, yeah. So in general, let me give you now a real life example. In general, see, even the digit example is a very easy example. Okay, the digit example is basically 784, right? And we reduced it to 200 dimensions. In real life, let's say that we have a cancer data, right? Which is typically a three-dimensional data. And the cancer data is, let's say, 1 million times 1. Okay, now a lot of it in the three-dimensional case, a lot of this data really doesn't contribute anything to the identification of the cancer. If there's a tumor somewhere there, we need to know, what to focus on. So if we did a PCA from 1,000,000 by 1, we reduced it to, let's say, 1,000 by 1, and then applied the classifier, we'll have a much better accuracy, no question, right? Okay, so now, one of the approaches that we do in deep learning is, so this is more like a hybrid approach. PCA has been known to us for the last 50 years, okay? So there's nothing new in PCA. Deep learning, on the other hand, is only 10 years old, okay? So can we do a better job, and I think maybe this is where you were coming to, can we do a better job with neural networks, identifying what is important rather than applying eigenvalues and eigenvectors? So now let me show you how that will be done. So I'm coming to now replace PCA with neural networks to do nonlinear PCA implicitly. Not explicitly, but implicitly. Okay, and this is a very important concept, especially if we go to an advanced deep learning course. You will be needing a lot of these ideas that we'll take a look over here. Okay, so let me give you an idea of it. Okay, so once again, was PCA supervised learning or unsupervised learning? Unsupervised because we didn't pay attention to whether the data given to us belonged to digit 2 or digit 5. We just computed the covariance between the data and came up with reduced representation of the high dimensional input space, right? Okay, so very similarly, the technique I will show you now is called autoencoders. Okay, autoencoder will do nonlinear PCA in an implicit manner, meaning we won't be telling it to compute eigenvectors, eigenvalues. Extremely simple technique, but does much better job than the PCA. Okay, and also this is a neural network. Okay, so we don't have to go and write the code where we are calling a library to do the PCA, then feeding it to a neural network. Everything becomes all one network, right? One neural network. Okay, so let me give you the idea of the autoencoder. Okay, so understanding the autoencoder, just like the PCA, the most important part is to understand what is basis. Okay. If anybody gives us the basis vectors for whatever dimensional space they are in, we can create data based on a linear combination of those basis vectors, right? Okay, so once again, take a look at a simple example of colors. We all know primary colors are red, green, and blue, right? For example, if you wanted to create a plain red color, okay, so pretend this is my vector over here, RGB. Won't it be this simply 1, 0, 0? Right? 1 times the basis vector in the red space plus 0 times the basis vector in the green space plus 0 times the basis vector in the blue space. Right? So 1, 0, 0 will give me the red color. Very similarly, can you tell me how will I create a yellow color?
0, 1.
Yellow, if you recall, red plus green makes it a yellow color. Okay, so it will be 1 times 1, 0, 0 plus 0, 1, 0, also 1 plus 0 times 0, 0, 1. Okay, so anyway, once we have the basis, like I said, so for example, if you wanted to create a purple color, right? There will be certain, maybe 0.23 over here,